Hello everybody, my name is Kyle Clocker. I am a PhD student at Oregon State University, and today we'll be talking about a sensor system and signal processing for automated blade collision detection on wind turbines. Let's begin. As we begin, I'd like to give you a bit of background on wind and wildlife management. Over the last 10 years or so, wind farms have been researched heavily for wildlife impacts and management strategies. Through this research, we found that the behavior of bats at wind farms, certain bat species are attracted to wind turbines themselves, and this leads to an increased mortality in these species. We've seen that the wind farms can be disruptive to certain migratory bird species and large raptor species too, as these wind farms are installed in their natural travel paths and in the paths that they use to hunt and gather food. Currently, management strategies involve using increased siting studies, that is, looking at a potential wind farm site before wind turbines are installed to determine the local environment that it will be installed in, installing deterrents on wind turbines, trying to deter away certain vulnerable species, and curtailment, which is the strategic shutdown of wind farms during periods of high environmental activity. The methods that are currently used to verify that wildlife involvement include additional site studies to observe the area after the wind farm is installed, to count the number of species around, and carcass surveys, which are surveys to study the ground to see how many carcasses can be found after the wind turbine has killed them, unfortunately. These studies can be a bit inefficient as they need a lot of manpower, and they do not lend themselves well to offshore wind development, where carcass studies are infeasible and siting studies can be much more difficult in an offshore environment. For that, we have developed a sensor system for on-blade collision detection. This sensor system features an onboard root module that includes several sensors to record vibrations. In this, we have a 3-axis accelerometer, a 3-axis gyrometer, and a contact microphone on board. Also attached to this is a camera which faces down the blade. These root modules are installed at the root of a blade, and the camera view faces down the blade itself. The goal of the camera is to have an automated detection of a collision event and then capture an image or a video of that event in hopes that biologists could identify the species that caused the collision. Through this, we could have a record of how many collisions happen a year per wind turbine, and we can have better understanding of the species that are causing these collisions in hopes to better identify and better understand the risk that they provide to the natural environment. This system was developed and then deployed on a 1.5 megawatt wind turbine at the National Wind Technology Center in Boulder, Colorado. 3 modules were installed at the root of each of the 3 blades and then connected together with a local wireless network for remote control and data logging. Through this, we were able to record vibrations from various wind turbine operations and simulated collisions. We simulated these collisions by launching tennis balls and small potatoes at the wind turbine blades as it was rotating from an elevated air cannon. Through that testing, we were able to acquire vibrational data from wind turbine operation and from our simulated collisions. The data that you get from any one recording is shown in the figure on the left here. In that figure, we can see that there are 7 streams of data per each blade. On each stream of data, the first one is a contact microphone, which records surface vibrations, and it is an analog voltage from this microphone that is encoded by AEC and then sampled at 2 kilohertz. The other 6 streams of data are the 3 axes of the accelerometer and the 3 axes of the gyrometer, which measure acceleration and gyration, and both of these are sampled at 200 hertz. Digging into this data, we can look into it and see what are some example collisions that we might find. And through this, we find that collisions are readily and typically very identifiable by the user. We can look through the data and, using our notes, readily identify collision events that happen on a wind turbine. The problem is that these collisions, their intensity that they show up on vibrational noise, their vibrational intensities that show up on the different sensor streams varies wildly with impact location along the length of the blade. In addition to this, turbine motion, operation behavior, and different weather conditions can induce a large amount of background vibrational artifacts. Shown on the left here is an example of a turbine motion artifact where the blades have begun pitching around to find a better spot to continue their motion in the wind. All of these additional sources of noise and spikes in the data stream make it difficult to programmatically describe how an impact should be. This prevents us from using a simple algorithm to detect impacts without having a large number of false positives triggering every time the wind turbine needs to move, or some weather event comes along that causes additional noise on the wind turbine. For that, we have a new collision detection process. The base of this process is preparing samples to be fed into some sort of machine learning algorithm, which would then perform the collision detection for us. We decided this problem was a good candidate for machine learning as the impacts can often be easily identified, but not easily programmatically explained in our old algorithms. So this process makes use of the accelerometer and gyrometer signals for collision detection. The first step in this process is to filter them with a high-pass filter with a corner frequency of about 5 Hz. The goal of this filter is to remove some of the vibrations associated with the base rotation and operation of the wind turbine itself. Then the signals are then windowed using a 1.5 non-overlapping window. Feature extraction is applied where statistical features are calculated on each window, and then each feature is standardized, removing their mean and setting the variance to 0. We then use these features to train an ADA-boosted random forest ensemble using scikit-learn in this case for collision detection. Feature selection. The features we chose come from a few different experiences that we've had while developing the algorithms for wind turbine detection. The first one is the window peak. This one comes from, as we did see some promise from using a simple threshold or a peak detection circuit algorithm for impact detection. In addition to that, we've included several statistical features: root mean square, standard deviation, variance, the kurtosis and skewness of the frames. These features are included as prior work by our colleagues have shown that these features in a machine learning environment are useful for identifying impacted collision events on a wind turbine. In addition to that, we're including 3 additional features that are from structural health monitoring applications, particularly for wind turbines. These features have been shown to help identify anomalous vibration activities in an operating system. These features are the root mean square entropy estimator, the crest factor, and the impulse factor. Again, all these features are calculated on 1 frame's worth of data. Each feature is then calculated on every axis of the IMU, and then after the calculations, we standardize the feature set, setting the mean to 0 and the variance to 1. From there, we need to select some sort of machine learning algorithm and approach to classify our data. From the field, we have 25 different recordings with simulated collisions. These collisions occur while the turbine is spinning at its operational rate. After windowing, this leaves about 1,200 samples to work with. Out of those 1,200 samples, about 69 of them contain data in which one blade on the wind turbine was struck. And out of those 69, 24 of them contain data which we can readily identify a collision that occurs on a specific recorded blade. And then the rest of the data are frames that do not contain any collision information. For our case, this is a very imbalanced data set, but additional data is very difficult and expensive to obtain. And we must protect a machine learning algorithm that can handle this imbalanced data set and work with the data that we are able to obtain. For this, we chose ADA-boosted random forest as it was selected due to its ability to handle imbalanced data sets and classify sparse events, as shown in other research. To train a machine learning algorithm, we first split our data into a 25%, 75% test train split. Samples were then labeled as positive if they contained an event where that blade was struck by a collision. All other samples were then labeled as a negative class where no collision occurred. We then dropped out the samples from alternate blades in a collision event. This means if a collision happened in a frame on blade 1, blades 2 and 3 of that same frame were dropped out of the dataset for testing and training. Then we trained an ADA-boosted random forest with 100 estimators and a max depth of 2 using the algorithms provided in scikit-learn. The receiver operating characteristic curve is done on the testing data, and it shows an area of the curve of 0.989. This area on the curve number is quite high for our algorithm, but we expect it to be quite high due to the great imbalance in our data set and the sparsity of positive events. To better evaluate our machine learning algorithms, we then present also the precision recall curve from the testing event, which also presents average precision of 0.809. This plot better represents the performance of the machine learning algorithm and its ability to identify collision events without having too many false positives. As I end the presentation, I would like to thank that this project was supported by the U.S. Department of Energy Office of Energy Efficiency and Renewable Energy. And I would also like to thank Jason Roadman and all the National Wind Technology Center staff and technician at the NREL's Flatiron campus where we tested. To conclude, we have developed and deployed and tested an on-blade unit for measuring blade vibrations and for automated collision detection. We then developed a collision detection process featuring the use of an ADA-boosted random forest model. This process shows positive results for detecting collision events without too many false positives. Thank you.